Oh. So you get to think of questions to ask. Any questions that you have from last class as well as the classes before? And if you don't, I will just teach you new stuff. Okay. Okay, so I'm back. I hope you guys had a good time when I was gone. So today I am going to take any questions you might have about the previous several classes. And then, as I mentioned, I'm going to do a fast-paced review of Markov decision processes and reinforcement learning, sort of from the planning perspective, from the deterministic planning that I have mentioned here. You may have, I'm assuming, how many of you have already done Markov decision processes and reinforcement learning in the intro to AI? Yeah, so most of you are supposed to have done it. The others who did not, they basically took a chance and they were going to make up. Basically, that's the IOU is coming to roost. I'm going to do a pretty fast thing. So I actually, the material I'm covering is sort of is covered over like what, 6 lectures in intro AI. And I think, no, maybe 5 lectures. I sent you the numbers, okay? So you can look at those if you want. You know, basically, if you don't know this material, it's kind of, it's, you know, you're going to miss out a lot. Okay, so I'm, again, as I said, some of you who are hearing it for the second time would be good because, you know, it's possible that you didn't get it as much in the first time, but I have to assume I can't do 5 classes of reinforcement learning and MDPs here. This is a graduate level follow on course. Okay, that's what I'm going to do. So I did my IIT Shindig and gave a talk there and got my little certificate and stuff. Came back yesterday, had a beautiful rainbow. How many of you have woken up and seen the rainbow in Tempe area? Okay, at least you did you wake up or you did not sleep?
At least
most likely you didn't sleep. Okay. I'm old and I had a jet lag. So it was very, very early in the morning. Such a beautiful rainbow. And then this morning I had this really fat baby hawk sitting right outside my window. So things are good for me. And then I remember that I have to teach. So okay. So the first thing is questions on anything that has been done. So just to give you an idea, what I'm trying to do here is with this class, I am hoping that you have enough of the background in planning, reinforcement learning, Markov decision processes, as well as human-aware planning, which is one of the other things that I'm very interested in, to start thinking about, you know, semester projects. Okay, while we do other things, and you know, from here onwards, we can go into deeper directions and specific things. But I'm assuming that we'll have the main common things that are needed to. I mean, in the beginning of the semester, I say, make up a project. I don't quite know what you're going to make up. Even now, it's hard, but at least you have like a fighting chance. Okay, So that's basically what my idea was. And I understand, again, the other thing is that it's, again, it's a graduate level course. I could make you read papers and act as if you understood. And you all do a very good job of acting as if you understood, because you're not supposed to ask other people questions and they won't ask you questions. That way, there's no rocking the boat. What I'm doing is I'm kind of going through like bunches of related pieces, quickly. And so you have to spend more time if you want to understand any specific thing. And so hopefully, in the project that you are picking, if it's a particular area, you may well find up reading more specific things in that area. This is how the world is going to be in general in graduate school. Okay, so getting everybody up to a certain level is what undergraduate courses are supposed to do. Graduate level MS first course probably also could do that, but these ones, we are also trying to do. We're trying to basically read more state-of-the-art papers and also get you to do some projects, and so you have to do it this way. Okay. And I think the other thing is somebody was asking, why can't we have? I think there was. By the way, there is a feedback link that I think I got like 2 or 3 people take time to kind of send me some questions or some comments. I mean, these are anonymous things, so you can always ask me what you want with your own name. But if you want to say things that you're worried will affect your grade, you should use that feedback link. And one of the things that reasonable question that somebody asked is, why can't we have more programming projects every week? Which would be good, except for everything there has to be, so certain level. If, for example, I think this person particularly hated having to draw the search trees. But the point is that there is no substitute for how, figuring out how an algorithm works than to either trace it or write it yourself. Calling the algorithm doesn't tell you how the algorithm is working. Right. And so, to some extent, that was part of the thing. And of course, we are doing very little of it. It's just to get you to at least go back and look at the lectures, which are pretty fast paced. I'm hoping that at least we make you to go back and look at some of the concepts that were discussed. And 100% is not possible. I mean, it's up to you. It's essentially in graduate level courses, it's really, as I said, it's partial satisfaction time. Okay, so you could say, I'm done with the course, I'll get some grade, or you can actually get like papers out, based on the projects that you've done in the class. And there's like a wide spectrum. Whereas undergraduate level courses are sort of more classical planning, where we kind of tell you, we have to do this, 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 and this. And if you don't do this, you fail. Okay, and if you do pass, then of course, you'll have some grade, but there is no such thing in undergraduate level courses. So you have to deal with that aspect of it, especially those of you who are undergrads. Questions? Yeah.
About last week's content.
Okay.
I went through the lecture again, and I didn't quite understand the concept of a minimally complete explanation. I was go through that.
Oh, the MCE, the minimally complete explanation. I actually don't have the slides here, but the idea in the case, the intuitive point about minimally complete explanation, I'll send you a longer message on this the class, is that after, basically in the example that he was showing, I think he was showing there about the fish walking around, right, and falling. So you could provide an explanation that just gets the person off your case. They say, why did you do this particular decision? That was the question, right? So a minimally complete explanation essentially is going to get the person off the back right now, except that is not a complete explanation. And in the sense that after you say this, they will ask more questions on the exact same decision. Okay, so that was approximately the point, but I will give you a better fleshed out example the thing. I don't have the example in front of me. So the point about this is that the explanations, I mean, so the version again is the one that's more general than minimally complete explanation is one where the explanation will not change. So there is a monotonicity property, and that's what it's talking about. But I know that it's a trickier point. I'll get back to you more clearly on the example.
Minimally complete explanation.
Okay, it's a good one. Okay, yes. Yes.
Just to confirm, when it discusses optimality of the robots plan, that is not in reference to its explicability.
I'm sorry, I didn't catch that.
When the homework is talking about the optimality of the robots plan, that's not, it's not the combined optimality of the plan.
No, it's just the optimality with respect to your life. Okay. I mean, one of the things that I think I was saying this towards the end of the class before that, and then of course Sharath went on to much more thing that in general life is much simpler if you don't have to deal with anybody else, right? I mean, it's also much less fun, but certainly much simpler, because you only have to deal with your own constraints, nobody else's constraints, nobody else's expectations on your behavior. Okay, so the robot can be optimal with respect to its model, without having to worry about whether or not that would make somebody in the loop be unhappy because they are expecting a different model for the robot. Yes.
I did some reading on the SECAN thing.
The SECAN, okay.
Yeah. So one thing that still confuses me. So you're using the LLM to give suggestions of actions that you could make. Basically saying, I want to do this task. What's your response to this? Does that not add a lot of complexity because you also have to kind of interpret what the LLM is trying to say?
I'm sorry, I didn't catch it. So basically what SECAN is asking is, I'm at this point, so what are all the options?
Yes, correct.
Yeah.
You're basically creating an LLM saying, I have spilled something, what do I do next? And the LLM is going to say, find a mop.
No, it actually does. Like it says, you can do one of 18,000 things. That's what LLM will say. And then basically they're trying to see which of them are actually feasible. Do you understand what I'm saying? So this was what, and there's nothing, I'm not quite sure what you mean by complexity.
You kind of have to so the LLM is still going to give you something that's understandable by humans. Correct? No,
it's not. I don't know. LLM does, first of all, I think that's, LLM is what LLM does. Right? It has no clue whether it's essentially trying to complete the next part of the passage. That's it. Okay. And the way it does essentially, again, we are not actually discussing, it's one of those situations where we're talking about LLMs without actually talking about LLMs in the class. It's like everybody may have played with them, but the idea is that when it is trying to generate the next word, for example, given some number of words, it essentially generates, it has a probability distribution of all the possible words, and it basically picks one of the maximum probability ones, right? And that's what it is doing right now. And I think the question then is, among the completions that it has, which one is actually corresponding to an action that is doable in my current situation? So for example, I'll say, I'm stuck at home, what can I do? And then LLM can say, you can fly, you can teleport, because all of this stuff basically are reasonable extensions of the text based on the web scale corpora. Somebody might have said in Harry Potter, somebody actually flew, from one place to other place. And so it has no clue as to whether that's a bad, physically feasible or not option. Okay. So it's, you are saying that it gives all these options, and you then have to see which of them are actually feasible in
but
your.
It's simpler to check that space of feasibility than doing a regression on everything in finding which.
So, no, it's still doing progression. They're not doing regression. Okay. So that's the other interesting question. One of the issues that I hope you will get as we go forward is The classical planning with the strips model is not very general. There are lots of problems that you may not be able to right away write in that formalism, but it has these algorithms that you wish you could use everywhere else. Like, for example, all goal-based reasoning should be doing something like regression rather than something like progression. But nobody does that because it becomes very hard in general MDP scenarios, which is what SECAN is looking at. It's looking at continuous MDP scenarios because the robot is in that scenario. In those cases, doing well-formed regression sort of techniques becomes very hard. So all it's doing is it's doing progression where you almost have to figure out which of the actions are still doable. And since you would have come up with many possible actions, or may you have come up, one of two things can happen. I'm stuck, I have no ideas. Remember, this is basically expected to be, you're acting as if you don't know the full space of actions that are possible. Okay, and so if you know the full space of actions possible, then the normal progression planner would actually just try one of those actions should be tried, and whichever of them is feasible can be tried. You may actually get yourself into your corner by trying that. Okay, here the number of actions. So either you don't know all the actions, or the number of actions is so huge that you wish somebody tells you what to do. Because then somebody tells you what to do, it's their problem, not yours. This is what I was saying when I was discussing. It's like, you're passing by, you got stuck somewhere, you could have tried more things, and stuck basically doesn't mean that there really is nothing you can do. It is that you got sick of it at that point. You don't really have any particularly good ideas as to what to try. It's like, if you're trying to debug a program, you're stuck. What does stuck mean? Did somebody hold your hand saying you no longer can type? In which case you're not stuck. You could try something, right? You sort of came to the point that I really have no good ideas. There are lots of ideas, but I don't have any good ideas. And so I'll ask somebody else, and they will say, okay, did you try this other thing? And then you just try. Okay, so that's what basically the LLM is doing. LLM can generate possible things that you can do as the completion almost of the prompt, rather than goal-directed tests. And whether or not it is goal-directed, and whether so normal planners, when they at least put all the actions as the possible choices, they check which of them actually take them closer to the goal. In SECAN, again, we are talking about a paper that we haven't looked at other than just discuss with one slide. In SECAN, they don't even try to capture the distance to the goal. They're actually trying to see, can I even do this action? And checking whether you can do the action is basically feasibility analysis. If it's a PDL thing, you'll just say, okay, I just check the preconditions in the state that I have and I'm done. And if you don't have a simple propositional state and you don't have a precondition effect kind of actions, then checking whether something is applicable itself can take time.
So it's relying on the LLM giving a sound response to the question.
What? It's not relying on anything. It's like I'm stuck. Like when I'm passing by and I'm stuck, and then I ask you passing me by and say, hey, do you have any ideas? I don't expect you to have sound ideas. I don't expect you to be complete. I'm not paying for any of this. So I just say, hey, do you try this now? Oh, sure, at least I try that. That's basically it. So it's neither sound nor complete. Okay. Other questions? Again, one of the things that you guys can do, I understand that it's once a week, and I think I more or less missed most of the office hours. There were a couple of times I was there, but nobody called in. But I think one thing you could do is right after the class, typically people tend to have questions. And if you haven't handled all of them, try to at least put them on the piazza. And otherwise it would be hard to, as easy as it is for me to say, are there any questions? I also know that that is the easiest way to say you all understood. Because most people, after a while they are thinking about it. and they're not thinking about everything, looks like I have no idea what question to ask. Okay. So when you are hearing something, it's a time that probably if you have a question, you should write it down. And then, if you don't either ask me or put it on the piazza, that would be a good way to handle it. Okay. Other questions? Anything else on this stuff? Okay. So what I am going to do, well, I put all these extra white sheets because there will be lots of questions and I have to write stuff. Okay, so I am going to do mark validation processes and reinforcement learning. This should be mostly like a rehash for several of you. It's unfortunately either you understood it and so it's going to be repetition, or you don't understand it, so it's not going to be enough for you to understand the whole area. As I said, if you really never heard of mark validation processes and reinforcement learning, other than as buzzwords, I suggest that you listen to at least those 6 lectures. Okay, minimum. That's basically that, that people who the fall 21 lectures. If you have learned it somewhere else, that's okay. You don't have to specifically listen to my lectures, but you should do something to get more hands-on experience. Okay, so I'll assume basically that I'm repeating this, okay, because there are a few people who haven't heard about it, but I can't, start as if it's like the first time, so I'll assume that you all heard about it. So I will make forward and backward pointers, even as I'm describing. So it's like repetition, the second time you're hearing this, okay. So I'll assume that you kind of heard of mark validation processes and RL, reinforcement learning, but I'm going to say a little more about it today. But in doing so, I'm going to connect it to planning stuff that we discussed till now. Okay. They're actually very closely connected. It's just that when people learn them, they learn them as if they're completely distinct areas. And so it's sort of one of the things I'll try to do is to kind of connect it to the A-star search and planning sorts of things that, Intro to AI talks about already. Okay, so sort of we figured out that strips and periodial planning, that's a factored or lifted version of the graph path search. Okay, understand what I'm saying. So you have a graph, and you're trying to, all of A-star search is trying to find the shortest path in the graph from one point to another point. What planning did is kept the graph search at the bottom and lifted it. Essentially, you're doing the search not in terms of the specific, in terms of the, not in terms of the complete state necessarily, but in terms of these actions which are specified in terms of preconditions and effects. And the states are not black boxes, they are in terms of state variables. That's what you've been looking at. Okay, there's a clear connection, but the connection sometimes becomes more surprising. For example, as I pointed out, regression planning corresponds to essentially parallelly making progress on multiple paths to see if any of those paths go to the initial state. Remember that. So it's not an obvious way to search. Okay. So this is why the word lifted or factored is something that you want to understand. So basically, it's not in the state, it's not in the black box state, it's not in the indivisible black box states. It is in terms of these actions with preconditions and effects. Okay. And you can do any amount of lifting. This is typically the whole thing that is done in logics, like you start with atomic states, then you could talk about propositional logic, then you talk about relational logic, predicate and relational logic, then you talk about first order logic, for example. Okay. Where we are right now, we are essentially just saying, basically we're going from atomic states to propositional logic. That's about it. Planning, the PDL looks as if it is relational, but if you understand the way logics work, basically predicate logic without functions can be easily compiled down into propositional logic. Just an exponential blow up. Okay. Once you have functions, the blow up becomes infinite. So you actually cannot compile logics with functions into the propositional level. Okay. So anyway, so we understood this, which is a generalization of graph path search. And then MDPs are going to take generalization of the graph path search to policy search. So the idea is this is lifted space. And this is atomic space. In the atomic space, you could be talking about graph path search. Which when you generalized becomes PDDL planning or strips planning. So the generalization is sort of in the lifted direction. Okay, you could also generalize the problem to MDP or policy search. In atomic level. And then the moment basically, so we are understanding this is a kind of a horizontal generalization if in this picture. Okay, MDP sort of, instead of saying let's look for the shortest path, they are looking for the optimal policy, where path is a special kind of policy. Okay, that's basically the idea you want to understand. And when you're doing this, you go back to the atomic level again, because you want to understand everything in the atomic level before you start understanding in the lifted level. Okay, and you typically are interested in the lifted space because essentially they are more compact representations of the problem. And it's also, there are like two possible reasons: compact, more compact, and more compact and easier for people to give, interpret. Okay, both are required. Both are actually useful things as to why people think in terms of lifted. Interestingly, in the old AI, both pieces were important. In the sense, when you do like strips planning, you're giving models as strips model, which is easier to do than like giving a big graph, and of course it's also more compact than giving the big graph. Whereas these are separatable if you wind up taking the graph path search and do your own generalization, inductive generalization. For example, representing actions as learned Bayesian networks, learned two-time slice Bayesian networks. There, they will still be more compact, but they may or may not be interpretable to the humans. Okay, so that's something that we have talked about before too, but that's something that we keep in mind. Okay, so what we're doing right now in MDP's case is we're going this horizontal direction and then trying to generalize the problem. Instead of just searching, here is the start state, here is the goal state, I will say, here is the state space. And every state has some reward. And you are basically going around from state to state doing your actions. And what you're trying to do is optimize, and so if you basically do like a behavior, until you die, especially if you have MDPs where there are terminal states, right? You keep basically walking around until you die. So then one episode is over. Okay, in that episode, then you have collected rewards in all the states you went through. And you add up, assume that essentially additive reward model. So you add up all the rewards, you get the reward for this trajectory. Using the same policy, that means, the policy basically tells you what you are supposed to do when you're in a particular state. Using the same policy, you again wake up and start walking around until you die. Using the same policy, you start walking around until you die. And every time you are getting some kind of a cumulative reward. And the MDPs try to find a policy that is a state to action mapping, which gives the optimal the maximum amount of cumulative reward you can expect. You understand what I'm saying? And because it also allows, the model also allows stochastic actions. Okay, one of the interesting things is if you do the same action the second time, it might have a different effect. Because these are all essentially, an action would be in the MDP scenarios, they are not deterministic actions. So you can toss a coin. Sometimes it comes heads, sometimes it comes tails. Heads with 50% probability, tails with 50% probability. If the robot tries to go in the north direction, 80% of the time it goes in the north direction, maybe 10% of the time it goes in the west direction, 10% in the east direction. And in this particular case, the robot at least is not going backward. You can also have a bad robot which goes 70% in the power direction and 10 in each of the other directions. Okay, all of these would be stochastic actions. And so the question is, just because the choice in MDP is Markov decision process, and so you are deciding, the agent is deciding what action to do. But the choice is only what action to do. The choice is not what outcomes should the action have. You understand what I'm saying? The action will have the outcomes it very well pleases. Basically, we'll see in a minute that you get to choose what action to do, and nature gets to choose which of the outcomes of that action will come. So in fact, MDPs are best seen as a game with nature. Okay, again, this already by now, some of you, at least the fall 2021 people should remember that, we went into MDPs from game tree search. Okay, so in the case of game tree search, there is an actual adversary who will try to, if you do an action, they will try to do their best to make that action have the worst possible outcome for you. Nature doesn't care. It doesn't care about you, right? So it's just a stochastic thing. So the action can have some various outcomes, and it just samples one of those outcomes. Okay, so you don't, basically there is no such thing as nature is out to get me. Nature doesn't care that you exist, right? Opponents, on the other hand, care you exist. This is my, the old example from the 471 that what is that thing? The Death Star, right? The Star Wars Death Star. Star Wars Death Star was pretty good design as long as nature is concerned. Because what's the likelihood that the nature would actually try to hit this Death Star in the one small part that is vulnerable? Harrison Ford, on the other hand, has the script in the hand and says, don't waste time, just go directly there. Do you see what I'm saying? That's the difference between games against nature and games against opponents who want to get you. Okay, so anyway, basically MDPs are games against nature. And so you try to do this policy search. So, and then MDP is a generalization of the graph search. And the difference in both cases, both in MDPs and the graph search, the model is given. The model in the case of graph search is the graph itself. The model in the case of, actually, graph search is graph and the start and the end states. That's the model. You need to tell what goal I'm supposed to achieve. The model in the case of in the case of MDP is the equivalent graph, except the graph is not a deterministic graph, right? When you are in a state and you do an action, previously, if you do an action, you get to a next state. That's the deterministic way of doing things, right? So in the deterministic case, if you are in state S1, you do action A1, maybe you'll get to state S2. Whereas here, if you are in state S1, you do action A1, you may go to S21, S22, S23. You see what I'm saying? So how am I supposed to put a link from states? In this case, I can nicely draw a graph where S1 is one edge, S2 is another edge, link them and write A1 as the edge name. right? In this case, essentially, there is no simple such idea because essentially, if I'm trying to draw this as a graph, then I have S1, and then in essence, there is a hyper edge. This is a hyper edge. So there is this idea called hypergraphs. Okay, hypergraphs connect sets of a vertex to a set of vertices. So the edge essentially connects it to a set of vertices. Okay, so MDPs essentially have underlying them a hypergraph structure. The hypergraph becomes a normal graph when the entropy of the distribution. So basically, these basically normally one of the other things you'll do is assume that there are actual probabilities associated here. So 0.7, 0.2, 0.1. So adds up to 1.0. So it's a probability distribution, right? And so you can talk about the entropy of the probability distribution. If the entropy is 0, then that means this is the least uncertain kind of an action. That means it actually tells you exactly what happens after this action. Do you understand what I'm saying? Like it's like imagine you have a coin, right, which has heads on both sides. So the outcome is deterministic. Is there any point in me saying, okay, I'm going to toss the coin? Can you guess? You see what I'm saying? Useless question. You see what I'm saying? So if the entropy is 0, then essentially that's the least uncertain kind of an action. If all entropies are 0, all actions have 0 entropy, then essentially you have a deterministic planning problem. The reason I'm doing this is, as I said, you would hear about graph search, you would hear about MDPs, and you would keep them into very different parts of your brain with make sure that there are no connections so that you will be freshly surprised that an idea which would make sense and you know it very well, if it's being used under a different name here, you would say, wow, this is a completely different idea. And that's not a good way to live. Okay, so that's what we're trying to do. Okay, so anyway, then you have the these models, both of them will have models given. In the case of MDP, the models will involve this sort of what do actions do, that's called the transition model. And you can think of the transition model as PSJ given SI and A. Probability that if you were to do action A in state SI, you will get state SJ. These probabilities exist for deterministic actions. They're just 1 in one state and 0 everywhere else. For stochastic actions, this is a normal distribution. It's essentially, splits the probability mass across all the possible states. And which is where we talk about higher versus lower entropy actions. The actions, so again, nobody would really like to live in an uncertain world. Okay, what we try to do is reduce the uncertainty. Right? I mean, basically, we stabilize the environment such that there's less and less uncertainty. They may not become completely deterministic, but in essence, deterministic is one extreme, and it looks as if deterministic and stochastic are binary, but really the less and less entropy you get, the more and more deterministic you become, essentially. Yes?
Can the level of entropy change?
What?
This sounds strange in my head, but like, is the level of entropy for a model constant?
No, I mean, no, all I'm saying is that the actions, each action, I mean, I can have 2 different actions I can sell you. Okay, one action is more deterministic. The other action is, low entropy, but not deterministic. Other action is very high entropy. Okay, so for example, if there are in a discrete scenario, if you have 100 states, and you're doing probability and you're doing action A in state S1, the most highest entropy will occur if the probability that you will reach any other state is 1/100. Right? That's basically what happens. And I mentioned this earlier that uniform distribution is the highest entropy distribution. Anytime it's more peaked, that it's not uniform, then that means there's less uncertainty. And this is actually connected again to information theory. I mean, basically, if I'm about to toss a coin and somebody comes, a friend of yours comes and says, I can tell you what the outcome of Rao's coin toss would be if you pay me some money. You're willing to pay them the maximum money if you happen to know that my coin is 50% heads, 50% tails. You would pay them the lowest amount of money, least amount of money, if my coin is 100% heads and 0% tails. Because why the heck would you pay money to people when you know the answer? If on the other hand, the coin comes 90% heads, 10% tails, you're willing to pay a little bit, not too much. And that's how the entropy and information are connected. Basically, when I'm answering the question, what happens after I do this action? How valuable is that answer? That depends on how uncertain is the action. You see what I'm saying? And again, before you used to think that, I think if you haven't thought about it before, like it's like deterministic versus stochastic, but then stochastic has degrees of stochasticity. And the particular thing is, a stochasticity, which is like this, is much more uncertain than a stochasticity, which is like that. Because the other one essentially kind of put more of its probability in this middle. Again, I have to draw it in such a way that the areas are always equal to 1.0, otherwise I'm screwed, but, so that actually doesn't look like that, but, you should take that into account, okay? Anyway, so when I'm talking about, in the case of PDL strips as well as the MDPs, the model for strips corresponds to the graph itself, S and G, start state, goal state. That's the model. Right, at the atomic level. And for this guy, the model will be these probabilities, which is called the transition model. And then RSI. There are variations of this, but RSI is the way to start with, which is reward for being in the state S. If I give you both of those, then essentially I have given you enough of a problem that computing the policy is a pure inference problem. Computing the optimal policy is a pure inference problem. It is useful in your heads to differentiate between pure inference, that is, the solution is in the deductive closure of the knowledge that you had, versus it's not a pure inference problem, it's actually inductive learning. That means you have to learn more about the world. Do you understand what I'm saying? Okay, so between MDP and planning, they're both essentially pure inference problems if you give the model. If you don't give the model, then it becomes a learning plus inference problem. Did you understand what I'm saying? So suppose I just said, here is the start state, here's the goal state. I have no idea what is connected to what, right? And I could have done that in this case too. I have an unknown graph structure. It's a deterministic graph, but it's unknown graph structure. Then I would call it reinforcement learning. It's just that reinforcement learning gets studied more often in this more general model. Do you understand what I'm saying? So basically, typically reinforcement learning textbooks start with MDP model as the expected atomic inference problem for which the model is not specified, and so they try to learn. But as we are doing RL, hopefully today, and if not, next class, you have to realize that whatever you're doing in RL can be applied to STRIPS planning too. If you happen not to know some of the preconditions and effects of the actions, for example. That's not knowing the full state space. You see what I'm saying? If you don't give the model, then it becomes learning plus inference. Typically, learning plus inference can just be also just learning. That's one of these interesting things we'll talk about. That's the difference between model-based RL and model-free RL. Model-free RL essentially just says, why bother about learning first and then doing inference? Let's just do the learning of the final product that you want, which is the policy. Okay, but if you have the model, then essentially it's just a pure inference problem. There's no actual learning. I mean, you can still call it learning. I mean, I learned what 4 plus 3 is. The very first time if you learned about numbers, you maybe learned 4 plus 3. But if you know arithmetic, 4 plus 3 is the deductive closure of arithmetic knowledge that you have. There's nothing new you had to learn. Do you understand what I'm saying? So it's worthwhile differentiating inference versus learning. And there can be deductive learning approaches where the learning essentially tries to improve the speed of the computation. Okay, those are the kinds of ideas called memoizing. Like, if you computed some result once, intermediate result once, and you store it so that you can reuse it next time, that will improve the computational speed. But that's still within the deductive closure of the original knowledge. Whereas if you learned something about, okay, if I do this action, looks like I also reached stage S5. I didn't even know this before. That's not in the deductive closure. You actually have to do it to figure that out. Okay, so reinforcement learning part is essentially, assuming that the model is not given, in which case you have to also learn the model. And that's a distinction between inference and MDPs. And as I said, RL can also be done in the graph model, but it's typically done in the MDP model. As like basically that is used. And then, as I said, since it's more general, MDP is more general, horizontally more general. Understanding learning within MDP kind of makes you understand learning within the graph search also. Okay. Confusing enough? Okay. So reinforcement learning is posed as a problem of planning where the model is not initially known. And in that case, you can either first learn the model and then infer the optimal policy, which is the model-based approach. Or you can say, hey, you want a policy, I'll learn you a policy. That's it. I go through the intermediate stage. That's the model-free learning. You guys know learning from examples, right? Just forget about sequential decision making. Learning from examples. Many of you, you know about supervised learning, right? I give you examples with their labels, and I give you a new example. You're supposed to guess the label, right? All the learning system is supposed to do is to guess the label of the new example after having seen the training data. That's it. Many learning systems take an intermediate step. They will first try to learn a hypothesis that is consistent with the training data, and then use that hypothesis to predict the label of the new data. Do you understand what I'm saying? If you do that, that's kind of model-based supervised learning. If on the other hand, you do something like k-nearest neighbors, where you never actually learned a hypothesis at all, Okay, you just, when you give a new example, you try to see how close is that example, what are the most nearest K examples to that example in the space that these examples live in, and then take the majority label of that. There you never learned a hypothesis. You see what I'm saying? So it's actually useful to understand model-based versus model-free in terms of this hypothesis. Do you learn a hypothesis before predicting test example labels or not? Okay, so if you have plus, plus, minus, minus, plus, plus, minus, plus, etc. Right? If you first of all learned a hypothesis, then you are kind of, in the case of plus minus kind of hypothesis, you're learning a decision surface. And then when you learn the decision surface, based on when the new example comes, you see which side of the decision surface the example lives. If you do K nearest neighbors, you don't do that. You just basically never learn any hypothesis. The hypothesis becomes the model of the data generation process. Okay, and the same thing happens in our reinforcement learning in the MDP case too. RL goes through a model. Essentially, that model can be used later, again and again. Whereas it can also directly go, just like the K nearest neighbors, it can go directly to the policy. What should I do in any given state? You can just learn that directly. At which point it has no model. And there are some advantages for both types of approaches, but it's possible to do that when you have, from a learning perspective, it's not necessary to learn the model anymore. Even though the pure problems are given with the model upfront. The MDP as a problem is given with the transition model and the reward model. And graph search as a problem is given as the graph model and the start and the goal states. Okay. Okay, so, and then the reason I'm kind of dragging you through this is that if you understand the relation between MDPs and graph search in this way, and I'll keep harping on this, then you can translate many concepts back and forth between planning and A-star search on one hand, and MDP and RL literature on the other hand. And it's worthwhile asking, what would it be in the deterministic case? In general, I tell my students that there are very rarely scenarios that the most interesting problems would be having a footprint in the deterministic case that is still interesting. The less interesting problems, they are trivial in the deterministic case. They only become actually interesting in the stochastic case. And so it's worthwhile asking yourself, if my problem wasn't deterministic, what would it be? Because sometimes the complexity of the world can be used to hide your own incompetence. Do you understand what I'm saying? You may not know how to fit a straight line, but you're doing this high dimensional data labeling. Okay, so it's worthwhile asking yourself, if you're solving a problem, what would its footprint be in the deterministic case? Okay. Okay, that's the thing. And then, I'll go through this in a minute again, but essentially because of the way I said this, you already know that reward is like the edge cost in the graph search. Except reward has the positive connotation, cost has the negative connotation, but it turns out that MDPs can either be specified in terms of rewards or in terms of costs. They're dual specifications. If it's cost, you minimize it. If it's reward, you maximize it. Just as normal MDPs typically tend to think of V and R. V is the value function, R is the reward function. The cost-based MDPs think in terms of C, which is the cost of being in that state, and J, which is the cost to go. And in fact, remembering that is very useful because V is just, if you kind of take into account this negative positive polarity, okay, then the value of a state in MDPs, which is like, those of you remember MDPs know that all the action is computing the value of a state. Okay, what is known? You're trying to compute the value of a state. You're computing the value, optimal value of a state. What is the optimal value of a state? You ask yourself, what would it be if the MDP had actions with zero entropy? That means it's deterministic MDP. If it's a deterministic MDP, what would the value, optimal value look like? What would it correspond to? In cost terms, in the cost formulation, it would correspond to the optimal cost of going from any state in the graph to the goal state. Did you get this, what I just said? Optimal cost of going from any state to the goal state. There is a name for this concept. What is it called? Again, this is what I'm hoping. This should be repetition for most people. If it's not, then then we are in trouble. Yes, go ahead. What heuristic? Optimal. I want optimal cost of going from the state to the goal state. You're close. What? No. What else is a qualifier for heuristics?
Perfect heuristic.
What?
Perfect heuristic.
Perfect heuristic. H star. Remember from the, I'm acting as if I just completed the intro to AI and I'm teaching this course. You just happen to have 1.5 years, you guys, and some of you, God knows how many years between the intro to AI and this. But if you think of H star, that's V star. You understand what I'm saying? Okay. So it's actually J star. H star would be J star because J would be the cost to go model. V is the benefit to come model. Okay. Okay. Cost is nothing but the inverse of benefit, and benefit is nothing but the inverse of cost. And the moment you think about that, then everything falls in place. And again, please understand this. I say this to my students that if you have a problem, ask yourself what happens to it in the deterministic case. Okay, just a sanity check. It won't be that because you know how to solve this deterministic question, you would necessarily be able to solve the stochastic question. There are all sorts of interesting. In fact, there are very few paradoxes in the deterministic worlds. There are tons of paradoxes, statistical paradoxes in the stochastic worlds. The Simpson's paradox, the whatever other paradox, and so on. Like the Monte Hall problem, Simpson's paradox. All of these are about stochastic worlds because we evolved to be very bad at uncertainty. It's a miracle that we're alive, right? Honestly, right? But we evolved to be very bad at uncertainty. We evolved to be very bad at disjunction. Like I said, that's why I was mentioning this earlier. You tend to visualize what we are saying, and I mentioned this in a couple of classes back. Visualizations are never disjunctive. So this is part of the reason why, essentially, if you say, somebody came, you more or less are likely to have imagined this person with a gender. I didn't tell you, but you imagine it anyway. Because it's very hard to imagine, a superposition of genders of this somebody, even though that's what I actually said. Because you imagined like a specific gender, you jump to a conclusion, you would then get into paradoxes. I never said this somebody is either a woman or a man or non-binary, but you made a decision. And so you will get into paradoxes. And you say, how did this happen? And I said, it's completely consistent with what I said. You just didn't pay attention. That's because I know that you are all bad at dealing with disjunction. That's why we need computers. Actually, the funnier part is our subconscious is extremely good at dealing with uncertainty. Otherwise, we wouldn't have been here like at all, right? Because given the way, how bad our retinas are and how bad our eyesight is and how hard it is to actually differentiate anything from anything in the real world in the forest, right? If you kind of see like a tiger and say, looks like a nice, small cat and try to kind of, pat it or something, your line has been cut off. you won't have any more descendants after that. Dead people don't have children. You see what I'm saying? Right? So subconscious, the visual processing, the auditory processing, etc., are extremely good at dealing with disjunction. Conscious is a different matter. Our conscious thought tends to actually go back to, jump to deterministic conclusions. Okay, but the point I'm trying to say is that sometimes the stochastic is just put there so that the problem has more bells and whistles so that any random solution looks impressive. Sometimes it's actually a hard problem, which in fact, even in the deterministic case, it's hard, in which case it might be worthwhile understanding how to solve it in the deterministic case. Okay. Okay, so RC is the edge cost, RC are the C. And R, so what I meant by RC is either R or C. R is reward, C is the cost. Either of them are sort of, C is the edge cost. V, value function, or J, the cost to go function, is basically H in the A star search. Because A star search typically is written in terms of costs rather than rewards. You could have an A star search in terms of rewards. There's nothing stopping you, but people think of graphs in terms of cost of the path. So that's what they do. And then V star and J star is H star. And you remember this, if you haven't thought about this before, if you remember this, many things start making a lot more sense in general, because they are not used in that particular way. And then optimal policy sort of corresponds to the optimal path. In fact, optimal path, I would argue, optimal path is the only non-trivial part of the policy for the deterministic version. That means if all your actions are deterministic and you are in start state and you have to go to the goal state, computing the total policy will tell you what will happen if I go to this random state. Why do you expect to go to this random state? If you found the shortest path, you do the action 1, you'll get to the next state. And action 2, you get to the next state. Action 3, you get to the next state. Last action will be the goal state. You declare victory, you're done. That's what's the beauty of deterministic world. So shortest path is an optimal policy, the non-trivial part of the optimal policy for the deterministic case. And similarly, Markov decision processes, people tend to talk about it as MDPs use dynamic programming. What does A star search use? It also uses dynamic programming. They basically both use optimal substructure. And these things sort of occurred in parallel branches. MDPs were studied in operations research, and A star search and graph search were studied in computer science and AI. Okay. And so that was the reason why they were not having, common terminologies. Okay. And then a couple of other things will come, which is finite horizon, and then I'll talk about in a minute. Finite horizon basically corresponds to depth limited A star search. Okay. And we'll talk about that again, but if I were, for example, if I have a graph search problem where edges have costs, each edge basically is an action and the edges have costs. Okay, then the cost bound is different from the depth bound. If I said, is there a plan of 20 or fewer actions to solve this problem? And among all the plans of 20 or fewer actions to solve this problem, which is the optimal plan? That would be bounded length graph search. Do you understand what I'm saying? It's a bounded length graph search. Okay, so you put a depth limit and then you do A star search on top of that. Okay, that corresponds to finite horizon Markov decision processes. So the idea when you put a depth limit is after you do those many actions, you don't get to do any more actions. You should have thought about it in terms of doing action. Everybody gets to do 15 actions. Those 15 actions cumulatively can cost only 15 units, can cost less than 15 units, can cost a lot more than 15 units. But the number of actions themselves are 15. And that's the limit I'm allowing you to do. Okay, now when I give a plan, when normal planning that we did in PDL, what is the depth bound? Did you give a depth bound? No, we basically just said find the optimal plan. So actually you have to, in those cases, you let the depth be either infinite or indefinite. Okay, so essentially you solve them with iterative deepening search style, iterative deepening IDA style, basically. The reason I'm saying this is you learn IDA style in one level, one place, and Infinite Horizon MDPs in a completely different part of the course, and you think these are completely different things, but they're all connected. And this is not just you, essentially people, because MDPs have been, as I said, studied a lot more in operations research and control theory. Those guys don't know anything about graph search stuff. And similarly, graph search people may not necessarily know anything about the control theory concepts, but they're all connected. It's what's very useful. There's a question.
Oh, I was just going to ask, is there a way to put a depth bound in PDL?
Yeah, you can. You can, in fact, there is an idea called bounded length planning. I'll show you in actually to see. There is an idea called bounded length planning, and because you asked me this, I don't know when to come. The class will get over by the time I get there. I said I wrote this thing, and this is not even half of the problems. But anyway, I mean, the thing that actually I don't even know where I kept this. Where the heck did I keep this? I don't know. I mean, I think I went away. So remember I said planning graph, you can find, I'll go back to where I am, and then I'll talk about the depth limited planning. And let me just go back. Just remember that when it takes half an hour for me to get through, then the thing is when I'm speaking, I go much faster, I believe. That's what at least I seem to delusionally believe. But anyway, so bounded length planning essentially is let's see, where was I? Oh, it's not even, I haven't yet come back. Like, okay, yeah. So remember the planning graph idea? We were talking about 2 classes back. I had the slide. I mean, I might come, I actually added it, but I may have hidden it by mistake. So you expanded the planning graph to level off. You can find the optimal relaxed plan. But you expanded, that won't be actually executable because it ignores the positive interactions. Now you also started doing the mutexes and you expanded it until level off. That means between 2 levels, there are no change in mutexes. This is the first level at which it is possible to have a plan. It may not be there, but it's possible to have a plan. Now you try to see if there is a subgraph of this planning graph that corresponds to a valid plan. That basically means not, the subgraph that you pick should not have any mutual exclusions between any actions that have been chosen. That is actually bounded length planning, where the bound is whatever is the level at which the plan graph leveled off. And most of the time what will happen is you'll try to search, you'll find there's no solution. So you expand it by 1 more level. Okay, when you expand it by 1 more level, notice what happened. You stopped expanding the graph because it leveled off. Right? That means there's no more new binary mutexes coming in between level K and level K minus 1 and level K. And I still couldn't find a plan inside. So then I expand it 1 more level. How do I expand 1 more level? I basically copy the entire damn thing, the last level once more again, because you know that no new mutexes will be there. The same ones that are there will still be there. All this allows you to do is now you increase the depth limit by 1. And then you look for the subgraph until you find the first place where you get the subgraph. That's how actually graph plan works. And in fact, this problem of trying to find the subgraph of a planning graph of length K, that's called bounded length planning problem. And it can be actually because that winds up being an actual NP complete problem. It's not P-space complete anymore because I know the length. Remember, the P-space completeness for PDDL comes because the length of the solution is exponentially large because of a Taylor of Hanoi in the worst case. But since I said of all the plans of length K, can you find me a plan that actually works, right? That is just essentially bounded length planning. And you can convert bounded length planning either into that graph search as GraphPlan did, or convert them into a bunch of, as I was saying last time, I believe, a constraint satisfaction problem or a SAT problem, and then solve those. And when you're doing that, you're doing finite horizon planning. Okay. Essentially, the finite horizon says after you use these many actions, you don't get to do any more actions. That's what the finite horizon part of it is. Okay. Yeah. What to do? Okay. Anyway, so I'm assuming that all of you know this kind of MDP picture already. You know, I mean, because all of my discussion was assuming that you know what an MDP is. And, you know, this is like the simplest example of MDP problem where, again, you have, you know, it's a grid. There is a start state, and then there is no such thing as a goal state. There's only rewards. Reward is strictly more general than the goals of achievement. The PDDL planning basically looks at goals of achievement. That means reach a final state which has a certain goals. And then we also talked about trajectory constraints such that while you are reaching the final state where the goals are true, make sure that the path you go through has certain useful properties. And when you do that, that are more general goals. And all such goals can eventually be compiled into the assembly language of goals called the reward metric. And just like the assembly language, nobody writes assembly language specifications. They actually write in the high level and compile it to assembly language. It is actually, even though at the atomic level, it is easier to think in terms of a reward metric, which is R of S. If you actually have a particular goal, what you are trying to optimize, it may or may not be easy for you to convert it into a simple reward metric. It's a one-way trap. For whatever you're thinking of, there exists a reward metric which captures that. Like for every high-level program that you can write, there exists an assembly level language program. But you only tend to think in terms of high-level language. And similarly, you tend to think of goals as a higher level specifications. Okay, so you could ask simple things like, how do I capture normal kinds of goals? And so one idea is, for example, this +1 and -1. These are essentially the +1 can be, if you don't have minus, if you just have +1, and then you put a rectangle there, what I mean is that's a terminating state. You get to that state, don't get to do any more actions. This is important because if you don't do that, you'll get to 1, come back, go back into 1, come back, go back into 1. It's like, there's a bunch of ice creams that are being given. You get to take one ice cream. And how do I ensure that after you take one ice cream, your turn is over? You're dead as far as your ability to collect ice creams is concerned. If I am namby-pamby about it, then the first person who reaches the ice cream just keeps on taking all the ice creams. You understand what I'm saying? Because the specification allowed you to take all the ice creams. Sometimes you want them to take all the ice creams and die, of sugar poisoning. Sometimes you don't. Okay, but the more general reward metric allows states to be visited any number of times. If you don't want the agent to visit that state ever again, you can't just say, be nice agent. You say you're dead. The moment you got to your ice cream, your turn is over. Your life in the ice cream queue is over. Okay, so that's how you capture the goals of achievement, essentially. And then, of course, here I actually also said this is a +1 state, this is a -1 state. Here, this is also a terminal state, but this is a terminal state with a large amount of negative reward. So here you die with sweetness in your mouth. Here you die with a lot of bitterness in your mouth. But you die both ways the moment you get to the state. If you don't want to die, you will avoid both the sweet and the bitter states. Which is not surprising because in the next slide, I'll show you that based on the reward metric, the optimal policy might be to avoid any terminal states, whether they're positive or negative. Because if you want to live a long time, right? If you consider that life is more interesting than ice cream, or the bitter ice cream or arsenic, life is more interesting than either ice cream or arsenic. You just avoid getting to either ice cream state or arsenic state because both of them will kill you. After that, you don't get to live. You see what I'm saying? Okay, so this is then basically in this case, I have -1 +1. And then I also said every other state I pass through as like a small negative reward. Essentially what I'm doing here in this case is I'm saying if you are just dilly-dally, then I'll give you a small negative reward. This sort of tries to specify my reward in such a way that your behavior is to try to go to the +1 as soon as possible. But notice that one very big thing to remember is it is not obvious how to convert the goal you have in mind to an RS. Every goal, every complex goal has a reward metric, reward function associated with it. But it's not at all obvious how to convert it to the right reward metric. I mean, basically what is the right reward metric? Which is where essentially the King Midas problem. How many of you know the King Midas problem? King Midas was basically, was going around and he said, yeah, so he knows. What is the King Midas problem?
King Midas' issue is when you touch things, it turns to gold.
Gold, exactly. If he touches anything, it turns to gold. And so he had a choice. He had a choice to ask the gods, what the gods came and said, what do you want? And he said, this is what I want. Whatever I touch, it should turn to gold. The god said, so shall it be. And you think, wow, that guy must be a rich, happy dude. But the problem is the actual reward metric didn't say that if I happen to touch my face, it should become gold. If I happen to touch my kid, they become gold. Gold means dead, essentially. Right? Organic matter, gold is inorganic, for example. So Midas essentially gets through life feeling extremely sad because he asked for a high-level goal, and the high-level goal actually got translated into a reward metric, which says, yeah, sure, for everything you touch. The reason he thought the gods will know what he had in mind is because he thought gods and he share the same common sense. Do you see what I'm saying? And the common sense says, when I say I want to, whatever I touch should become gold, I don't say that if I touch this can, the water in the can, the drink in the can becomes gold. That's not what I mean. Whatever I touch, unless there is additional reason for it not to turn into gold for my survival, then please turn it into gold. That's what I mean. Okay, now Stuart Russell essentially is very, very worried about this because he thinks that, this is the problem with RL reward metrics, because the reward metrics essentially what you have in mind and what the reward metric that the robot is assuming might be completely inconsistent. And so that will get you into safety problems. systems. You basically are giving a goal to your robot, and the robot essentially, it's incompletely specified goal. And we always specify goals incompletely. We assume common sense. We assume common sense on the part of the listener to complete it in a reasonable way. Or at least ask, saying, are you sure everything, really, everything you want me to convert into gold? The guards basically want to teach this guy a lesson, and so they said, sure, whatever you want. Actually, there's another version of it that I like even better, where this other guy, this Indian guy, was praying to Brahma, who is another of the Trinity guards, and then please praise, and the guard comes, and then he says, okay, what do you want? And he says, oh no, before I ask what I want to ask you a couple of questions to figure out how this whole Brahmalokam, the Brahma's world, works. And he says, is it true that every rupee, whatever the dollar in your world is worth $1 billion here? He said, yeah, that's our currency is very high, very powerful. So then he says, okay, I want 3 of your dollars. And he says, I'll be back in a second. Did you guys get it? Because, normally, commonsensically, if his dollar is worth billion of dollars here, his second is likely to be billions of years here. And so the guy says, I'll come back in a second, and you're screwed. It's not your second, he's talking about his second. So again, in all these cases, essentially the reward, the goal you have is not specifying it in the exact way is quite hard. It's possible. So what MDPs do is assume that somebody has already converted it into the reward metric, and I'll do the inference on it. And since converting into the reward metric is hard, there's a whole bunch of work right now in the reinforcement learning community trying to figure out how to make sure that what the agent thinks are the human's goals are actually the human's goals. So enter alignment problem. Because, if there is making sure that actually what the humans have in mind when they gave the goal is the same, is closer to what the robot is interpreting as the goal. Okay, and so that becomes a big issue. We never thought about it. We assume that in planning, you say, this is your goal, I'll just do the goal. But if the goals are specified in high enough level language, you'd assume people know what they want. It's actually a bad assumption because people really don't know what they want. But if it is a high level language goal they have in mind, and then there is a reward function, the assembly language is what you use in doing your optimal policy, there is more of a chance that there is misalignment between the specified goal and the reward metric you are actually converting it into. So you would then have to start learning the reward metric, which normally reinforcement learning assumes doesn't have to be learned. In fact, the pure reinforcement learning requires basically the probability, the transition probability, PR probability of S, the Sj, given that you're doing AI in Si. And it also needs RSI, which is the reward metric. Now, in the pure reinforcement learning problem, the agent goes into the state, the reward washes over it. So it doesn't need to be told what is the reward of being in this state. It's like, it's like me telling you, you have no taste whatsoever, and I say ice cream is good for you. That's no fun, right? You have inbuilt taste, and that's sort of hard-coded. And so essentially, as soon as ice cream touches your tongue, you get a huge dopamine release. On the other hand, as soon as you hear the word Markov decision processes, you don't get a high dopamine release. So you have to learn to get a dopamine release anytime you hear MDP. You see what I'm saying? That's called an acquired taste. What is an acquired taste? Acquired taste is to convert things that are not obviously concerned with your inbuilt reward circuits into something that you consider rewarding. That's an acquired taste. I mean, come on, how many there's this nonsense about good tasting beer. Dumb idea. I mean, there's a beautiful Simpsons episode where they start doing the Springfield says no alcohol, and the Duff beer says, we know people like the taste of our beer, no problem. And then they'll become non-alcoholic Duff. And then next frame, they close the factory. Let's not kid ourselves. I mean, nobody really likes the taste of beer. They associate the tipsiness and all the other fun stuff to this and acquire a taste for beer. Do you see what I'm saying? So the reason I'm saying this is learning rewards is normally not needed in reinforcement learning because you're supposed to feel the reward directly. But if you're trying to learn the rewards of somebody else, so that the policy you're doing is not only good for you, but also good for them, like the human aware planning you talked about. Do you understand what I'm saying? There you need to learn that reward. And it's not obvious to learn what is making them happy. Because they don't know how to specify it, you need to try to learn it. And it's actually reinforcement learning plus plus. Basically, actually, I would say the normal reinforcement learning is reinforcement learning minus. Because you think that you should learn everything except reward washes over you, so you don't have to learn reward. But when you are trying to learn reward of the humans, then you need to also learn that. And that will be like a normal RL. But that part is now, if you're just learning the reward, people call it inverse RL. Makes no sense whatsoever. There's no reason why it should be called inverse RL. But that's what it's called. Because normal RL typically assumes that as soon as you go to the state, you'll feel the reward, so you don't need to worry about it. Okay, let's take a 15-minute break and then continue. Okay, so that was the MDP that we were talking about. There's a reward metric, and the reward metric here is actually being specified in this way, that every state has minus 0.04 reward, except the states that have actual numbers, and those have +1 and -1, and they are terminal states. That's what I said in this case. And so you can talk about how to convert that reward and into optimal policy. Right? One of the things that we make a big deal about, what the heck is that? Yeah. Okay, so basically MDP is atomic model for stochastic environments with generalized goals, because any arbitrary goal can be converted into a reward metric. In fact, this is pretty obvious, but last NeurIPS, believe it or not, last NeurIPS, the best paper award went to these people who said, for a wide range of arbitrarily complex goals, it's fairly easy to convert it into a reward metric. Remember, I said there is a reward metric, but you may not be able to be sure exactly what you have in mind. This is like the assembly language issue. Okay. In fact, it is easy to fall on your face. For example, if you just, in the case of classical planning, if you want to write classical planning as an MDP, right, then what you would wind up doing is you would give the only state where the goal is true. I mean, all the states where the goals are true, you give them, you make them terminal, and you give them cost 0. And everything else has some uniform cost. That means for each action, assuming that each action, has one cost unit, then you would say every state transition has uniform cost. And the final state transition, if you wind up going into any of the goal states, you die with just extra cost 0. And then optimal policy will make sure that you will die with the shortest path. Do you understand what I'm saying? So this is actually worthwhile thinking about how would I do classical planning as an MDP? Because it's more general, so it should be doable. Now, if I ask you a slightly different question, which is instead of classical planning, I have many goals. I have n goals. And I have actions with costs, and the goals, each of these goals gives me a utility. I mean, if I do this goal, I'll get these many points. I'll get this goal, this many points. And what I'm trying to do, and assume that the utility and the costs are the same units. This is not actually true, but assume that's the case. Then this is deterministic planning problem. All actions are deterministic. They are just weighted actions, costs. No, the actions are not uniform costs. They're all different costs. And goals don't all have to be done. But if for every goal you do, you get some points. In fact, you don't have to do any goals. This is what is called partial satisfaction planning. That's what graduate school is, as I said. So there are all these goals. If you do the goals, you get the points. I'm feeling lazy. I don't feel like getting any points. I'll just sleep today. That's fine. That's a valid plan. It's a valid plan whose utility happens to be, whose total utility happens to be 0. Because you didn't get any, you didn't do anything, so you didn't waste any actions. And you didn't achieve any goals, so you didn't get any. So there's no cost, no benefit. You're a 0 bar person. But it's possible that actually, if you do certain number of actions, you would have able to achieve like a subset of those goals. And then you take the utility of the subset of goals, subtract from it the costs of the actions you took. That would be the utility of that plan. I want to find the optimal such plan. This is partial satisfaction planning problem. It lives very much in between deterministic planning and MDPs, where I did change the action stochasticity. Actions are still deterministic, but I changed the goal metric. Do you understand what I'm saying? That people tend to forget that the MDPs generalize both the action dynamics, which is stochasticity, and the goals being basically generalized goals. Now, if you're trying to solve partial satisfaction planning problems as an MDP, this is as simple as it gets. I mean, it's not even like King Midas problem. I told you that there are all the goals, and whenever you achieve the goal, you get those points. And if you achieve 5 of those goals, you'll get cumulative of those points. And then if you did these actions while doing them, then you subtract the cost you done. This is what you do, right? I mean, you get certain amount of money in your pocket and you're trying to buy different things you buy, give you different amounts of pleasure. And you're trying to figure out, what to buy. Right? That, if you write it as an MDP reward metric, it's actually not obvious as to how to convert that into a reward metric. Because the most obvious thing would be to say any state where any of those goals are true are terminal states. That won't work. Because the moment you get any one goal, you're dead. The other thing is, since the terminals are not going to work, let's make nothing non-terminal, everything non-terminal. If you make everything non-terminal, that also won't work because you can keep on going to that goal state multiple times and keep getting more and more reward. But the idea is that my expectation when I said these are the 15 goals and you can, you decide which subset you achieve and you will get the utility of those subset. I didn't mean that you keep achieving the same goal many times, you get more points. Right? That's a very reasonable specification. Do you understand what I'm saying? Now you can't make them terminal, you can't make them non-terminal. What do you do? You see what I mean? This is as simple as it gets. I'm not even talking about King Midas problem. It turns out that the way to convert this into a reward metric is to add to basically double the state space. Okay, so in essence, you want to have an extra variable called done. Done says I'm done. I'm not going to collect any more rewards. Okay, and after you decide you are done, that's when we count the rewards you collected. If you do that, then you can correctly convert over partial satisfaction planning into an MDP problem. We had to do this one time because we were actually writing, I'll give you the link to the paper, but we basically came up with what we considered a better algorithm for partial satisfaction planning in PDL framework. Who do you compare it to? There are nobody else doing partial satisfaction planning. So we said, well, it's an MDP problem. So if you try to solve it as an MDP problem, how will it work? And to do that, you have to convert it into the correct MDP problem, the correct reward metric. And once you do this, then you can use any off-the-shelf MDP solver and jump up and down with joy because they all die. Because atomic solvers suck. You see what I'm saying? Assembly language sucks mostly. Okay, so atomic solvers basically are not very good. So MDP, the kind of heuristics we are using at the higher level, partial satisfaction in the PDL level, were much more powerful than anything MDP will do in the lower level. And so we could then make happy curves saying we do better. Do you understand what I'm saying? This is just trying to tell you that something that you think is a reward, a goal, converting into a reward is not obvious at all. In this particular case, it involves doubling the state space. Which is something that you want to remember, right? Graduate study is at once extremely easy and extremely hard compared to undergraduate. Extremely easy if you don't care about it. If you just want a feasible path out, pretty much anything is a feasible path. Finding an optimal, I mean, by graduate study, I mean PhD, by the way. I mean, MS doesn't really count. Let's not kid ourselves. Okay. Whereas if you are, sorry, I lost my thought. So if you are doing optimal policy, then you are looking at an MDP which is double the size of the MDP corresponding to maybe an undergraduate, for whom they say, these are all the goals you have to achieve all of them. You feel, my God, they're being unfair to me. They're making me do stuff, but electives are hard. Choice is hard. Because the moment you have choice, I can hold you responsible for not making the right choice. You see what I'm saying? You need a brain to deal with choice. And this is where actually the Simon Sant, did I mention Simon Sant in the class? Everybody should know Simon Sant. Okay, what is Simon Sant? You know, Herbert Simon is the only guy in computer science to have gotten a Nobel Prize. Why did he get it? Because he actually got it for his work in economics. And Herbert Simon essentially, Newell and Simon you were one of the 4 people who did the original Dartmouth Conference on AI. And Newell and Simon did the GPS, General Purpose Problem Solver. Actually, they did Logic Theorist. I did this whole thing. I wrote this whole thing in the Piazza. Logic Theorist, which was doing theorem proving by mean sense analysis, which works for theorem proving because there are no negative interactions. We went through this whole thing, right? And then they can generalize it to general purpose problem solver. Then strips people tried to copy it and they became incomplete because there are negative interactions. Anyway, Herbert Simon essentially has this allegory of an ant on the beach. And you're an observer, you're looking at the ant. And you see that ant direct, instead of just, you would think that going from here to here, straight line path is the simplest path. Anybody who does very complicated path must be extremely intelligent. They must be doing it because there is a reason. They must have thought about it. So if you look at an ant, right, going from here to here, it's jigging and zagging and doing zigs and zags, etc., blah, 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 and then it reaches someplace. And looking at the kind of that path, you would say, wow, this ant must be one of these high quality GPU ants. You know, it has like humongous inference being done. But the ant is the original Roomba. It keeps walking towards one place, hits itself, turns one side. You see what I'm saying? So the apparent behavioral complexity might actually be because of the environmental complexity conjoined with a stupid organism. You see, the ant basically has much less choice. It just keeps walking until it hits and then turns. We actually can change the beach. We have choices to actually get rid of the beach and make it like all flat so that you can do straight line paths. And then, so the question is that a good thing to do? Is this optimizing the overall reward metric of the humanity? Choice is hard. Okay. So anyway, basically converting reward oversubscription planning, converting partial satisfaction planning, ESP into an MDP requires doubling state space size. I should give you the paper for that. But anyway, so that's sort of to make that point that writing reward metrics are hard. But once you give the reward metric, you can find a policy that's optimal with respect to that reward metric. Do you understand the difference? Okay. It's just that I'm optimizing something. Is that the one that the human wanted me to optimize? That's the $1 million question. Okay. So anyway, you get rewards for visiting each state. Objective is to increase your cumulative reward. Now, what is the solution? That's what we are trying to figure out. That's what MDPs are trying to figure out. So, it basically looks like a state to action mapping. Okay, state to action mapping. In fact, here itself is an interesting question. All policies for optimal policies for MDPs will be deterministic. This is a loaded word. The actions are stochastic, but the policy itself is deterministic. In any given state, you just know which action to do. In fact, it's actually more interesting than this. It turns out that a generalized policy for an MDP will say for every state, here is the distribution over the actions. You sample using that distribution, do an action. That would be called a stochastic policy. Do you understand what I'm saying? It's called a stochastic policy. There is no obvious reason to believe that an optimal policy for MDP will also be a deterministic policy for MDP. It turns out there's a deep theorem that shows that for the normal MDPs, if there exists an optimal policy, there will also exist a deterministic policy with the same expected value. Which means if you just stick to deterministic policies, you don't lose completeness. This goes out the window if you generalize MDPs to Markov games. This is Markovation process. You have a more generalized version of MDPs called Markov games, where you actually are no longer playing against nature. You're playing against what Siddhant knows. You're playing against an adversary. A human adversary. I mean, intelligent adversary. Doesn't have to be human. Intelligent adversary who has choice and they can exercise their choice. Nature basically doesn't know about you. It doesn't care that you exist. So it just basically samples from the distribution. Your opponent, on the other hand, samples from the distribution such, it doesn't sample randomly from the distribution. They will pick the outcome that will be the most negative for you. So if you're doing like cybersecurity scenarios, which is what Siddhant does, was doing at any rate, that's basically a Markov game. So you have actions, you are putting some, defenses to secure your system, and the attacker is trying to get through the defenses. You understand what I'm saying? And if you don't like that, then rock, paper, scissors. You're playing rock, paper, scissors with somebody else. You pick a deterministic policy, you die. You lose, not die. You lose. I mean, I think I mentioned this and I should send this to you guys again, but continuing my Simpsons examples, there is this cartoon strip where Lisa and Bart have to make some weighty decision as to who gets the ice cream, last ice cream or something. And they decide, okay, we'll just play rock, paper, scissors. And then there are these bubbles on top of Bart's head and on top of Lisa's head. And Bart is saying, ooh, we get to play rock, paper, scissors. And Lisa says, ooh, we get to play rock, paper, scissors. And Bart always picks rock. The moment you know that you always pick rock, I mean, I hope anyway, I know that there are students who may not actually know rock, paper, scissors. The interesting thing about rock, paper, scissors is there's a circularity. There is no such thing as one thing always wins. If I know what you're going to do, then I can always defeat you. The usual thing about rock, paper, scissors is both of you simultaneously make, what you're picking. And there are rules, random rules saying paper covers the rock. I never understood that. I mean, it's like, as if rock becomes like very mellow the moment you cover it on paper. I mean, I'm pretty sure I can put paper around rocks and throw it at you and you won't like it one bit. But, those are the rules of the game. Those are the rules of the game, right? And so the interesting thing about rock, paper, scissors is if you construct a deterministic policy, it cannot be optimal. By definition, any deterministic policy will be defeated. So you have to consider stochastic policies. In fact, for all the games, the policies would be essentially for each state, there is a distribution over actions. And then you select with respect to your distribution, and the opponent selects with respect to their distribution. As long as these are non-degenerate distributions, if any of them are degenerate distributions, then basically you can defeat the opponent, because typically the optimal policy, if there is an optimal policy, it doesn't have to be deterministic. Whereas for single agent playing against nature, if there is an optimal policy, it will also be for every stochastic optimal policy, there is also a deterministic optimal policy, which has the same value. Okay, because of which you can just think in terms of deterministic policies. Now, here is a twist. Now that you understand this whole background, you realize that you don't have to search in the space of stochastic policies, which is much bigger. Because, by the way, let's think about how many policies are there. Okay, if in an MDP, there are S states, and let's say there are A actions per state, maximum A actions that you can do in any state. How many policies are there? How many distinct policies are there? In the first state, you can do one of A actions, so there are A possibilities. In the second state, you can do one of A actions again, A squared. Third state, A cubed. Fourth state, A power 4. So the total number of policies is A power S. That's finite. At least it will be done bad, but it's finite. If on the other hand, I said stochastic policies. How many stochastic policies are there? Infinite number. Right? Because for every state, it's not an action being picked, a distribution over A actions being picked. There are infinite number of distributions over A actions, because corresponding to, how do I, suppose I just have two actions, just two actions, right? What are the possible probabilities that each of those actions can have? Infinite number, right? Because there's basically P will be the probability of action A1, 1 minus P will be the probability of action A2. P can be between 0 and 1. Every continuous number between 0 and 1 is a probability, corresponds to a different distribution. Right? That means there are infinite number of stochastic policies. Nobody in the right mind would ever consider searching in the space of infinite number of stochastic policies when they can get completeness in searching just this finite number, but big but finite number of A power S policies. Would you agree? Then you would be wrong. Because if you consider ideas such as policy gradient, which we may or may not talk about, but no, I'm giving you, policy gradient is a way of, essentially policy gradient corresponds to plan space search in policy space. Remember when I was talking about planning, I mentioned LPG, the local planning graph, where you basically guess a plan, find the flaws and tries to reduce the flaws, basically extend the plan to reduce the number of flaws, and then pick the best neighbor and then continue doing this. This is hill climbing search in the space of plans. Policy gradient does continuous hill climbing in the space of policies. I feel sorry for Josh, but I mean, by the way, knock on wood, WhisperNet is out, and apparently it completely writes down even my accent into correct English. Like I think somebody was tweeting, I think Andres Karpati was tweeting his first 3 minutes. The guy speaks even faster than South Indians like me. And he's tweeting that he took 1.5 minutes of his lecture and gave it to WhisperNet, and it only made one mistake. It said Bengio with a J instead of Bengio with a G. That's it. So I don't need Josh anymore. I mean, I can convert it into English, and then somebody has to read it. And so I will have GPT-3 read it, then we can all take a holiday. But anyway, so the point is policy gradient. I should probably try to write this down somewhere. Where do I write it? Let's see. Keep and new slide layout. This is the reason I don't write anything, because it takes time. Okay, good. Okay. So let me write down this stuff. Interesting. Number of deterministic policies for S state A action MDP is A power S. Number of stochastic policies is infinite. Okay? Policy gradient search does hill climbing or continuous, actually hill climbing, continuous hill climbing. Hill climbing, also known in some circles as gradient ascent or descent, in the space of policies directly. So this is like LPG, Revini et al., which does plan space search by hill climbing, taking number of outstanding flaws as the goodness metric. Okay, so, but now you want to do continuous, but doing gradient descent is not feasible in a discrete space, right? There are a power s policies, a discrete number of them. To do gradient descent, the underlying function that you're doing gradient descending on should be differentiable. So it means it can be continuous. So surprisingly, so you say, okay, we will gradient descend in the space of stochastic policies. Strange nonsense, but makes sense, right? Even though deterministic policy would be enough for finding the optimal, since you're trying to do gradient descent, you act as if you're actually searching in the space of stochastic policies. And then you can actually do empirical gradient estimation and then make a step in the direction of the steepest gradient and do gradient descent. So here you do this for very different reasons than Bart and Lisa's case. When Bart and Lisa had to do stochastic policies because without that, they can't be complete. They can't even find the optimal policy. Here you're doing stochastic policy, even though that deterministic policy will be optimal, because searching in the discrete space with gradient descent is not easy. This is one of those cases where you are trying to make everything look like a nail because you have a hammer. And your hammer you want to use is gradient descent, so you want to convert everything into. In fact, one of the complaints that people like Jan LeCun have is, we have nothing against logic. I wish it is differentiable. Again, it's like, we have nothing against your head. I wish it looks like a nail because I have a hammer. Right? And there's nothing wrong with that, essentially, because you have that particular tool and you want to use it. Okay. So that's kind of an example of what I'm hoping as transcription of the notes. So, but anyway, so continuing along. Okay, what's the solution? It's a number of policies. You're searching in the space of policies. And one of the things I want to remember is that want you guys to remember is that in the case of MDPs, you are still in the static world. There's no additional agents. You are assuming fully observable world. Because during the execution, the state is fully observable. That's how you look into the table and say, if I'm in this state, what is the action? Okay. In the case of normal MDPs, you are still assuming instantaneous actions. Actions can't take time. If actions can take time, it will become what is called semi-MDP. Semi-Markov-Adhesion process. Okay. And it is allowing stochasticity. It's not just deterministic. It allows stochasticity. And it does allow partial satisfaction. The goals don't have to be full satisfaction. Those are the only changes, stochasticity and the partial satisfaction. And people will jump to thinking that MDPs are actually dynamic, MDPs are partially observable. No. there is an MDP, which is partially observable, which is partially observable MDP, POMDP. And it turns out that to solve POMDP, which is what we were having a discussion in the background earlier, that POMDPs basically don't know which state they are in. That basically means they are searching in the space of belief states. Belief states is what is the probability I think I'm in this state versus this state versus this state. Even though you may not know what state you are in, given the actions, given that you know the actions probabilities, even if you don't know the initial state, even if your initial state is a set of states, after doing the action, you can get a new set of states and the probability distribution over there. That will be a new belief state. And so POMDP policy would be essentially solving POMDP is like solving MDP, except in a slightly bigger state space. In the case of partial satisfaction, solving partial satisfaction planning was just solving normal planning, except double the state space size. In POMDP, it's just like MDP, except the number of states is not the number of states, but the number of belief states. How many belief states are there? When in doubt, always say infinity. There are infinite number of belief states. So POMDPs are solved as MDPs in the space of belief states. And so that actually tells you that the size of the policy that they're computing, the size of the policy they're computing is going to be the number of belief states, at least. For each belief state, you need to know what action to do. In the worst case, there are infinite number of belief states. Remember, we said classical planning became P-space complete because we had, it unfortunately gets to do Tower of Hanoi. And Tower of Hanoi can have an exponentially large solution, because of which it can't be in the class NP. In the worst case. Now, POMDPs are trying to compute the optimal policy for a state space, which can be infinitely large. So in the worst case, your policy would be infinitely sized. That means every different belief state has a different action. I mean, in the sense that multiple different belief states might well have the same action, but there's no locality. In this region, all of these guys will have action A. You understand what I'm saying? What that basically means is what would be the complexity of solving optimal policy for POMDP. Worst case complexity. It has to be undecidable. As in the worst case, you have to compute an infinitely large structure. I'm doing complexity by dimensional analysis in this class. I'm not actually doing gadgets and proofs. I'm just saying, if your worst case solution can be exponentially long, you can't be in the class NP. If your worst case solution can be infinitely large, you may never get them. POMDPs are actually only solvable in cases where locality of the belief states come into play and saying all the belief states in this region, this is the action. There, the policy would at least be compact. Do you understand what I'm saying? So I actually thought of this crazy example when I was talking to these guys in the middle, which is, think of the following analogy. You all know that in the end, in real courses, I don't know whether that happens in this course or not, a cumulative grade point is there, cumulative number of marks you got, which is between 0 and 100. And then that will be converted into a letter grade. That's the grade policy. Right? So everybody has a grade policy. Now, if I just told you that, basically, how many policies are there? I mean, all I said is that every cumulative grade corresponds to a letter grade. Nothing more. So that would actually allow for 39 being a C and 30 being a B. There's nothing wrong. I just said each cumulative corresponds to an action. How many grading policies are, what would be the size of the grading policy in that case to fully specify the grading policy? It will be infinitely large because there are infinite number of continuous numbers between 0 and 100. For each such number, I get to specify a different grade. So in the worst case, my grading policy is infinitely large. The grading policy description, not the number of policies, mind you, just the grading policy description is infinitely large. Then you say, nah, it's not going to go anywhere. Let's put some locality. Locality basically says things like contiguous. I mean, there are things, the obvious things that you're talking about, which is you cannot have inversion in the grades. There is A is bigger than B is bigger than C is bigger than D, and a lower cumulative grade, a cumulative point cannot get a better grade than the higher cumulative. That's a constraint. The moment you have that constraint, the grading policies can be specified in the language you have learned to love or hate, which is grade cutoffs. Each policy can be just computed in terms of 4 grade cutoffs, if there's ABCD. Right? That's the kind of issues that come into play when you are computing policies for MDPs. Because in the worst case, actually, MDP is undecidable. Okay, anyway. Okay, so the simplest way to solve without actually looking at optimality is to actually play this MDP as an online game against nature. So you remember the min-max trees from the intro to AI, except it's like min, I mean, instead of min-max, it is expect-max trees, expect and max. So you essentially get a choice of doing what actions. The nature then decides which of the outcomes of that action occurs by sampling probabilistically without trying to do any, I mean, there's nothing personal. Nature doesn't care that you exist, so it just samples from the distribution. And then a new state comes, you know which state you are in. This is like, when you're playing game, then after the opponent makes their move, you know the board position. So after the nature picks the move of the particular outcome of the action that is actually going to happen, then you know what state you are in, the exact state you're going to be in. And then you again decide which are all the actions that you can do and pick one action. And so then it will get you like a tree like this. So here, I'm in like 3-2 cell, I can do go right, go up, go down, go left. If I do go right, I can with 0.8 probability, I go to 4.2, 0.33, I go to 0.1, 3.3 cell with 0.1 probability, 3.1 cell with 0.1 probability. Okay, and nature gets to pick which one actually happens. So during planning, you don't know which one will actually happen. So you can only take expectation. Right? If it turns out that all of these actually know the values, these are all the terminal states and you know the values, right? Then you essentially can take these values, take the weighted sum, that will be the expected value of this action. And then there is an expected value for this action, expected value for this action, expected value for this action. And this guy then picks the maximum of those expected values and says, that's my action. And just like in min-max, the deeper you go, the better off you are. Because here I stopped here. And one of the things was 4.2 is actually terminal state. So you know that it cannot get any reward other than -1. Because there's no thereafter, no future after that. Whereas 3.3 and 3.1, they're just intermediate states. They're not done yet. The game is not over. So when the game is not over, remember what happened in the chess, the min-max. You take an evaluation function. That's a heuristic way of evaluating the board position. The dumbest idea is to just say, I'll just take the immediate reward as the value. The other is to actually do some kind of a heuristic, some particular heuristic. So for example, you can try to compute the heuristic value of, how far this is from the goal or something. And then use that as the initializing value and then take, just like the evaluation function, and then use that to do your online optimization. If you do that, you are essentially doing MDP problem, MDP policy, you're computing, you're not going to be optimal, just like you're never really computing chess optimal policy. Nobody's computing chess optimal policy, they just want to win. And that's one of the things that I did mention to people in the intro to AI is you would think that chess is much harder than things like Rubik's Cube or 36 puzzle. But finding optimal cost path for 36 puzzle or something is extremely hard compared to even chess. Because you're not trying to find optimal policy for chess. You're trying to win the game. You understand what I'm saying? There's a big difference. So, whenever it's a game situation, you're not talking about optimality, you're talking about being better than the other bozo. And for machines, the other bozos are us. They can do better than us, they win. But the optimality of the 36 puzzle, there is no opponent. Right? It's a mathematical theorem. You have to be able to say that this is an optimal, here's the guarantee that this is an optimal path, path to solve 36 puzzle. And so actually that's much harder. Finding the chess optimal policy would also be hard, but we don't ever look for that. Okay. So this is a way you can do online policy construction for MDP, and this way of doing it is called Rtdp, real-time dynamic programming. You think this is a dumb idea? It's like it can't be this easy. Because MDP is a big deal, it can't be this easy. Well, it's close to state of the art in terms of solving large MDPs. The one that is actually state of the art for solving large MDPs is just a small variation on this called MCT. Monte Carlo tree search. What does that do? It instead of in the way min-max as well as this is done is kind of decide like a depth cutoff and then look at all the nodes in that depth and try to evaluate their value. In the MCT, you just keep playing one line of play. Okay, so when you come here, rather than say this is 0.8, this is 0.1, this is 0.1, you sample. You know that nature is going to sample. So you sample it as if you are nature. So you have to actually toss a three-sided coin, which comes outcome 1 with 0.8 probability, outcome 2 with 0.1 probability, outcome 3 with 0.1 probability. And then actually toss it and see which one it comes and then take that as the direction you're going. And you can toss coins in programming, right? Random seed generation. Right? Okay, so once you do this, then you take an action, toss coin to see what the outcome will be, then take another action, toss coin to see what the outcome will be. And each time the coin that you're tossing would be a different coin because each action will have a different probabilistic outcomes. Until you actually reach one of the terminal states, if possible. And when you reach the terminal state, that is a deep probe to a terminal state. At that point, the terminal state's value, the reward, is the only reward you get. Then you can back up this line. You understand what I'm saying? The only problem is that you are essentially trying to do this backing up of the values. Backing up is the only game in town in online search. Okay. In the MCT, what you're doing is you're backing up over single probes. In Rtdp, you are backing up over subtrees. Okay. Now, interestingly, when you're doing MCT, one worry is which action are you choosing? Remember, when you're choosing the action, you don't know which side to go. Do you understand what I'm saying? Because you're picking a probe. What if every time you pick the same action? Then the probes are all going to be in one small region of the space. Okay. So you might actually have some kind of a heuristic reason to pick these are a better action kind of a thing based on some heuristic calculations. But you have to try actions that haven't been tried more often. If you don't, then you are likely to not actually get the best backed up value. Because in the worst case, if you keep on picking only the first action, the leftmost action, let's say, every time, that's definitely not going to give you, there's no reason to believe that that will give you the optimal policy. Okay. So weirdly enough, this requires an exploration of the kind that we will again talk about. And you have, if you're done RL, you know that you have to do, reinforcement learning systems at any given point of time have to try things that they haven't tried before, because if they just optimize with respect to the model they have, that model is incomplete because they haven't seen the entire state space yet. When will you actually see entire state space? If you do infinitely often, actions, then you will see entire state space. What you would like to do is sort of be greedy in exploring, except provide some exploration so that you don't always pick the most promising action according to your model. And so with some epsilon probability, you pick the greedy action, and with 1 minus epsilon probability, you'll randomly pick an action. That's what RL, exploration exploitation trade-off, is. In the Monte Carlo tree search, you have to do the same kind of thing. You have to pick directions that haven't been picked often enough. And the nice thing, actually, there is some discussion of it in, in fall 21 class, but this, in the class, we actually, I think we had like 3-slide description of the MCT stuff. But it's a nice technique to know. There's a nice idea called upper confidence bounds, which kind of can be used to set an optimal exploration strategy, which sort of tells you with what probability should you pick the less promising actions. And it's kind of connected to how often have you gone under that action. Any action under which, it's not surprising that if there's a particular action under which there are many, many probes that were taken under that action, and there's this other action by which there's not even a single probe taken. Looks like a dumb idea not to see what is happening there, because what if that actually has a hidden shortcut? You don't know. Right? So if you do MCT and you do online computation of the best policies, that's pretty much the state of the art for MDPs. That's what AlphaGo does. It actually does a game, but it basically still doesn't see. So the question is there this way of doing things? You don't have any guarantee that the policy you constructed is optimal. You're constructing policy action by action. right? Just like you play games, you're actually playing game against the nature, you do an action and then, so using this, you figure out what action to take. I hope you understand what I'm saying, that first you think, you're thinking during the thinking time, you are either doing Rtdp or you're doing MCT, multiple probes, in different directions. And then back up the expected value under each of the actions. And then pick, and then you say, okay, I'm time to act now. So you pick the action that has the best expected value. You do it. When you do it, then the nature tells you what actually happens. Before you are supposing, you are sampling. But nature sample is the only thing that matters, not your simulation of nature sample. Once you do that, now you are again playing a next round with the nature, just like games. Okay, but this is like an online construction. The question is, can you do basically offline construction of an optimal policy? And that's what you actually first learn in MDP lectures, which is the value iteration and the policy iteration. Okay, even though there are very nice ideas, it's more to understand that there are optimality guarantees. Nobody ever does value or policy iteration, except the folks in operations research community. The guys in the IE, in the industrial engineering, they do it. Why? Because industrial engineering people actually are the ones who came up with MDP formalisms. But they very carefully formulate the state space of the problem such that the number of states is very small. If the number of states is small, then you can say I am optimal with respect, for this MDP. You, on the other hand, if you're trying to, for example, do RL on Atari games, which is like a big deal that people have gotten into, right? Essentially, the state is a pixel map. Every possible pixel value change is a new state now. Like a different way of hanging yourself. Previously, you can have a state, you start in terms of belief states, you hang yourself because there are different number of belief states. You have an abstract state, but you took a picture of it. And pictures can change in one small pixel, that's a different state. But even if you don't do it, then in general, basically the AI tech people tend to say, let the problem come without too much hand coding of the hand formulation. Or people say that why not? So in fact, did I mention this already? My example that OR people sell their programs and their grad students together as a package. Okay, mere mortals can't use these OR packages. You need our grad students. That's how the grad students get a job. Right? And AI people say, we don't need anybody in between. We'll just sell you the the software. And so as long as you have new software to be developed, you have jobs, after which you won't have jobs. Who needs you? Right? I mean, you're thinking, hopefully I'll die before that. And so it's like the third generation's problem, not mine. But that's basically what AI folks do, which is they don't think in terms of selling this with a middle person, the middle grad student. So the OR guy will come, talk to you, figure out what your problem is, figure out what's the best formulation in terms of the state space, then gives it to the underlying MDP with, maybe like 200 states max. In fact, normally like for the longest time, for POMDP, the state of the art for the optimal policies for the POMDP is this thing called the tiger problem, which has 8 states. Because it has 3 Boolean variables. Each state is defined in terms of 3 Boolean variables, 2 power 3, 8 states. You see what I'm saying? So, I mean, And then that's what these OR guys might do, for example, that they will try to get the number of states down by removing all the irrelevant nonsense. And so they can actually solve it to optimum. And in comes the AI guy, he says, I have this camera, I'll take picture of the states. 8 states all of a sudden become infinite number of states. You see what I'm saying? Then optimality is a dream. But as I say, computer science people should understand what it takes to be optimal before giving up on it. Right? So that's why you actually look at value and value iteration. And at this point, I'm going to actually say, since obviously I didn't get up to all my slides, I'm going to actually make those of you who don't remember, in fact, everybody can actually look at those lectures that I mentioned, at least the MDP part of it, for the value and policy iteration, okay, especially value iteration. But essentially what you will wind up doing in the value and policy iteration is basically, here is the way to think about it. In the case of value iteration, you have an MDP like this. You're trying to compute value V star. Computing the value V star is like computing H star. H star is never computed for A star search problems because it would be a dumb idea. You are solving a deterministic problem starting from state S to go to goal G. But if I said I want at once the optimal path from every state to the goal state, that is all source, single goal, shortest path algorithm, then that is a direct comparison to MDPs. There, the way you would compute them, the way you would compute all source shortest path algorithm for a single goal would be to essentially compute H star. That means for each state, you compute the optimal path length from that state to the goal state. Once I give you H star, then you can convert it into the paths. Because if I know H star for every one of the, if I know H star for every one of these states, then I need to figure out, let's say I'm in this state, okay, and I need to figure out what action to do. Assuming it's deterministic, let's say I can do action A1 that takes me to S1, which has H star value of 0.7, H star value of 7. I can do A2, which will take me to S2, which has a H star value of 20. Since H star is cost, and if these are the two actions, what would you do? You would pick the 7. So you greedily pick the action which takes you to the state with the highest and with the lowest H star value. If you're doing values, you do it in the reverse. You greedily pick the state, greedily pick the action that takes you to the state that has the highest V star value. This is all assuming that somehow you computed V star, right? If I did compute V star, converting V star into pi star, which is the optimal policy, is very simple because you do greedily best action at every point. Now you'd say, no, Rao, you just told me what to do for the deterministic case. What happens if I have stochastic situation? No big deal. In the stochastic situation, action A1 can take you to S1 with this probability, S2 with this probability. And action A2 will take you to S4 with this probability, S5 with this probability. So you take the expected H star for action A1, which is P1 times H star of S1 plus 1 minus P1 times H star of S2, and compare that to, P1 dash times H star of S3 plus, 1 minus P1 dash times H star of S4. That would be checking which is the what will give you the best expected value greedily. To do this, you can convert V star into pi star. Then that leaves you to figure out how to do V star. And you will look at the lecture, but it's actually very simple. It turns out that I take you in the lectures, and the normal way people do this is to take you to 2 steps. One is first think of finite horizon MDPs. A finite horizon MDP basically says you only get to do T number of actions. T is the horizon. That's like bounded length planning. Right? And so if you do T actions, then what I can do is I can ask myself, basically in that case, the policy, it turns out, again, you have to think about this. For those of you who remember this already, should not be surprising. The policy for finite horizon case is more complex than the policy for quote unquote infinite horizon case. Because in the case of finite horizon, what is the best action for you to do in any given state depends on how old you are. Ford said that for a young person below 30, the only investment should be in themselves. That means you should basically, whatever money you have, you just put it on yourself, not to eat ice cream, but to probably start Ford factories. That's what his idea was. But notice that it is a policy that is specific to your age. Why? Because there is some random thing about me. None of us seem to be living beyond 100. So we have essentially like an upper limit on the number of years we can live. And so your optimal policy depends on how much time you have left to go. Right? So basically the policy for the finite horizon case will actually be one policy for each number of levels left. If you have 0 levels left, what's the best policy? If you have 1 level left, what is the best policy? If you have 2 levels left, what's the best policy? And then you actually look at your state and the number of years left to go and pick the action. This is the finite horizon case. And it turns out that computing the optimal value for that is very simple. Because if you have 0 time left, then the immediate reward of the state is its value. And then if you have 1 time left, then everybody at the 0th level, they have their true values, you back it up. You do this k number of times, you get the optimal value for the finite horizon case. You'll get the optimal V star, and then you can convert it to pi star if you want. And the more interesting case is if you have infinite horizon, that means you can live infinitely long. And the weirdest thing is if you live infinitely long, your policy is smaller. Because it doesn't depend on how much time you have left, because you always have infinite amount of time left. It's like the Hilbert Hotel. Which essentially means that the policy can only say, if you are in the state, this is the action. So there'll only be like a V star would be just as time, the size of state, number of states. And the way you actually compute V star is act as if it is a finite horizon case and keep doing 0, 1, 2, etc. until the value doesn't change from one level to another. Then the value has converged. When the value has converged, it becomes V star. When it becomes V star, you can convert it to pi star. That's basically value iteration. And I basically gave like very fast overview of maybe 2 lectures, if you have never heard of MDPs. And maybe at least 1 review lecture if you have heard of MDPs. Okay. And then you can come back, we'll talk about this as well as reinforcement learning and and then connect it back to planning. Okay, thank you.
Oh, that's the easy part. See, my brain thinks in growth. That makes sense.